Hi, I'm Rico, and my final project is the score-based diffusion model for molecular generation. Firstly, let me give an introduction of what does this project do. In this project I utilize a score-based stochastic differential equations, which is a model to achieve stable molecular conformation generations. And this project uses the QM9 datasets, which includes 100,000 stable molecular conformations represented by automatic numbers and Cartesian coordinates. My method centers on variance exploding stochastic differential equation, VESDE, for training the model, along with the trainable equivalence graph neural network PAI, and to efficiently predict reverse SDE scores. The diffusion model is kind of a generated model which has gained extensive attention in generating high quality samples in recent years. The core concept of this model involves modeling the data distribution as a process that evolves over time following a stochastic differential equation. And this evolution is marked by the increasing variance of data points as time progresses. This mass equation is basically to get the three coordinates of the molecule. Xt represent the data point, and fxt is the drift term that dedicates the deterministic part of the evolution. Gt is the diffusion term that controls the magnitude of the stochastic component. Wt is the Wiener process. For the training part, training this VESD model involves learning to reverse the diffusion process. The model is trained to denoise corrupted data samples, essentially mastering the reverse dynamics of the SDE. The reverse process can be described by the reverse time SDE, which can be solved using methods such as the Euler-Maronian method. Once trained, the sampling from VESD model involves simulating the reverse time SDE, starting from a noise distribution, usually Gaussian noise, and evolving it backward in time to generate a sample from the learned data distribution. Since the coordinate space of molecules is continuous, I use the diffusion model to generate the three-dimensional conformations of molecules. Here's the main code for score-based model. And this PAIN neural network is designed specifically for molecular modeling and predictions. Is to incorporate interaction models from physics to better predict the physical and chemical properties of molecules. Here is the code for verifying the equivalence of PAIN, and this is the architecture of it. And so for the main code, the first step is to load the trained PyTorch Lightning model and repeat the definition of four identical elements to generate the molecule 4 times. And this is sample molecules from Gaussian noise by reversing the SDE using the Euler Maronian sampler. This is a total of 500 sampling steps. And here is the visualization of the three-dimensional conformation of molecules, in which the green represents carbon atoms, white represents hydrogen atoms, blue represents nitrogen atoms, and red is the oxygen atoms. The result shows that my model can generate diverse and stable structures. Our molecules satisfy Lewis' rule and conform to chemical intuition. So there are three main parts that I think can be improved with better environment or better data sets or equipment. First is to improve the scalability and efficiency of this model. And the second is to expanding the data set to include larger and more diverse molecular conformations. And the third is it would be great if this can integrate this experimental data. And by pursuing these future directions, I think it's feasible to enhance the capabilities of the molecular conformation generation model, transforming it into a more powerful and versatile tool for scientific research and industrial applications.